law was what? Whenever two systems are in equilibrium with the third one, they'll also be in equilibrium with each other, right? That was the 0th law of thermodynamics. Now we are going to start with the first law of thermodynamics. So this says that, see, internal energy, I've already discussed it with you. Work done also I've discussed it with you. Internal energy we did in so detail, I think in kinetic theory only we did it, or even in thermal properties we did internal energy. So whatever is the total heat added to your system, it is the sum of your internal energy as well as the work done. This is basically what is your first law. So it is based on conservation of energy. So this law statement is whenever heat is added to a system, it transforms to an equal amount of some other form of energy. Fine. So heat is added to the system, increase in internal energy plus external work done by the system, right? So if system absorbs heat, you will have to use all these conventions, sign conventions class. In your question, in your exam, it will be given to you as, let's say, 5 joules. Whether it was going to be minus 5 joules or plus 5 joules in your calculation has to be decided by you. So how will you decide? You will decide based upon the sign conventions. If your system is absorbing heat, you will write it as positive. Whether it's given positive or negative, you will follow these sign conventions. So if your system absorbs heat, you will write heat as positive. And if your system is releasing heat, emitting heat, you will write heat as negative, despite being or whatsoever is the magnitude of it, whatsoever is the sign. Just take the magnitude from the question, apply sign convention by your own. In this formula, no, for putting it. I am repeating this because this is very important. Vaziha, am I audible to you? Vaziha? Vaziha, let me know if I'm audible to you or not. All right, so total heat will be, so it can be positive and negative. Now, same thing, if temperature is increasing, temperature of your system is increasing, you write the internal energy as positive. If the temperature is decreasing, then you write it as negative. And whenever expansion is done, so work done is positive. And if you're thinking your system is getting compressed, so work done will be negative. Okay, Vazia, all right. So all these sign conventions you have to apply in this single stated formula class. Please understand this fact, because it can happen in your question. Energy is given as, let's say, minus 5 joules. And your system is absorbing heat. So you will not put it as minus 5 joules. You will by yourself put it as plus 5 joules. Got it? So you will have to apply sign conventions on your own. Let me show you a question, then you can note down all these. It says that if 1 gram of water at 100 degrees Celsius is converted into steam, fine. If volume of steam is 1671 centimeters cube, you have to find out the change in the internal energy of the system. And L, remember L, we did it, latent heat. So latent heat for steam is given to you as 2256 joules per gram. So what do you have to find out? You have to see from this, no, delta Q is equal to delta U plus W. You have to find out this. This is unknown. So how will you write delta U? You will write it as delta Q minus W. Now, how will I get delta Q? My work is to find out delta Q. If I get delta Q, if I have work done, I'll subtract it. I'll get the change in internal energy. So change in heat will be ML. Remember, we did it already in thermal properties. This is latent heat of fusion, latent heat of vaporization. So here latent heat of vaporization of steam is already given. Mass is also given 1 gram. So 1 into 2256, that will be 2256 joules. So among these, I have got the value of this. Now work done is still unknown. In the last class, I have told you how to calculate work done. Work done is simply, if your pressure is constant, work done is pressure multiplied by the change in volume class, right? So what will be the work done? See, do we have this much data with us? So atmospheric pressure we have to take because this is converted into steam and pressure is not given. And volume is given to us 1671 meter cube. Right, but we do not have the initial volume. This is the final volume. So what we can do, we have the mass of water. We know the density of water. So we can calculate the volume of water. See, for this part, no. Volume V2 is 1671 centimeter cube. So V1 will be what? Density of water is 1 gram per centimeter cube. And mass is also given 1. So volume will also become 1 centimeter cube. Now we have all the data with us. So pressure, we'll take atmospheric pressure 10 to the power 5, or let me take it full properly. 1.01 into 10 to the power 5. 1.01 into 10 to the power 5 is the pressure. Now change in volume. 1671 minus 1 into 10 to the power minus 6, this much whole meter cube, because I've converted into meter cube. So this will become 1670 into 10 to the power minus 1, or simply 167 joules. So look here, class. Now I have got the value of this as well. So I'll subtract this. Delta U will be simply delta Q, that is 2256, minus W, that is 167. So this will be 2089 joules. Do you understand how do we solve these types of questions? Heat can be calculated using ML or MC delta T, whatever is given. Since here state was changing, we used latent heat. Right? If the temperature would have been changing, we would have used specific heat capacity. Then work done, I have told you P delta V or P dot dV integral, depending upon the question. So calculate them separately, take out their difference, that will give you the internal energy change. So, okay, note it from here, note down both these parts, then we'll move on to the thermodynamic processes. So four thermodynamic processes are there. See, the three quantities are there: pressure, volume, temperature. So if in your system the temperature does not change, you will say the process is isothermal process. If the pressure does not change, see here the temperature is not changing. If the pressure is not changing, you will say it is isobaric process. If volume is not changing, you will say isochoric. So three processes. This is based on temperature, this is based on pressure, this is based on volume. When these three quantities are constant, these processes occur. Now, if heat remains constant, then you say it is adiabatic. Adiabatic, I have told you in the last class as well. On Friday also, I have told you adiabatic. Thermos example also I have given. Then you have non-cyclic process and cyclic process. So this also we have discussed. A non-cyclic process is one in which system does not return to its initial state. Like this graph we had seen, PV graph. Then cyclic state also we had seen where it returns to its initial point. All right, so note down the names of these processes and just one line. Then we'll move on to work done. P delta V, no, PdV, that derivation, which that formula which we have, we'll see a small derivation for that. Just note it down, then we'll see that. See, work done's derivation can be done by, you will take a cylinder, you will attach a piston onto it. Now, when you will apply pressure from inwards, so what will happen? This will get displaced. So this will be, there will be a displacement that would have occurred. There would be a slight displacement, right? So let's say A is the area of the piston. P is pressure. F is force exerted. So now look, work done, this will be force multiplied by displacement. That is what is the formula of work done, no? Force into displacement. So force into displacement is this. Now look here, class. Pressure is written as force by area. So force can be written as pressure into area. So I'll write the force as pressure into area. Now see this. Area multiplied by the thickness. Area multiplied by thickness gives volume. Area multiplied by thickness gives volume. So work done becomes PV. PV, P delta V. So this is just the derivation noted down. These points you have already noted down, class. For expansion, for compression, all these points, area under this, you have already noted down. So just note down this derivation part, just this part. The first law also we have covered. It's just that I have told you, CP, the specific heat capacity at constant pressure. This is written as P. And specific heat capacity at constant volume. This is written as V, CV. So CP by CV, you write it as gamma. So wherever you will see this gamma, no, it means CP over CV. Just write these 3 points. I think you already have written it, but just rewrite it. Then we'll move on to isothermal process. See, so when temperature remains constant, that thermodynamic process, we call it as isothermal, right? So let's say initial temperature is there, final temperature is there. So when the initial and final temperature equals each other, we call it as isothermal process. So whatever change, there won't be any change. Heat change will be 0. That means T2 minus T1, this will be equal to 0. So what are the conditions for isothermal process? Conditions for isothermal process. So first is that the walls should be conducting. And the process should be slow. Fine. And again, one thing, during expansion, system will absorb heat. It absorbs heat. And during compression, system will reject heat. Fine. So these are the basic points. Now work done. Work done during isothermal process. So we'll start with this. Work done is integral of PDV from V1 to V2. Now PV is equal to nRT. This we have seen, PV is equal to nRT. So what should I write the value of P? See class, from here P will become equal to nRT divided by V. So put it nRT dV over V integration from V1 to V2, because these three are constant. See, number of moles is already constant. This universal gas constant is already a constant. And here temperature is also a constant. So all these terms are constant. Now class, whenever you have no integration of dV over V, you write it as, see this is nRT, you write it as log V from V1 to V2. All the time this dv over d, whenever you have no dx over x integral, that becomes log. Fine, log from x1 to x2. This is the generalized rule. So this will become nRT log v2 minus log v1, v2 minus v1. And one more thing also class, when we write no log a log minus b, whenever we write it as log a minus log b, this is always written as log a divided by b. So this will become nRT log v2 by v1. Now see, when you'll put all these values no to convert log into the base of 10 so that you can use proper log table. So we write this as 2.303 nRT log base 10 V2 by V1. Now you can directly use this formula the way you have been using log table simply. If just in case you have pressure na class, this derivation does not come. So just remember this formula directly, but just have a look by chance if it comes in your exam. If pressure is there, so 2.303 nRT log P1 by P2 it will become. Here it was V2 by V1. This becomes P1 by P2. Reason is that, see, P1 V1 is equal to P2 V2. We know P and V are inversely proportional to each other. So if V2 is here, from here you can say P1 by P2 is equal to V2 by V1 from this. That's why instead of V2 by V1, I'll write it as P1 by P2. Fine. And apart from this, one more thing class, see, delta U will be 0 here. For isothermal process, your internal energy becomes 0. So if you put it in the first law of thermodynamics, no, delta Q is equal to delta U plus W. This term becomes 0. So all your heat is equal to work done. This is valid for isothermal only. This is valid for isothermal process. This is from first law. This is from first law of thermodynamics. Fine. So numerical, I'll tell you later on. First, note down these points, then I'll tell you this numerical. This is an easy numerical that we'll discuss. Note it down first. It should be slow because the temperature will have variations then. All right, the temperature, for the temperature to remain same, if the process is slow and wall is conducting, then only whatever molecules are getting transferred, they'll remain same. Whatever molecules are at one end, they'll travel at the other end. So if the process is very fast, then the temperature will also change. And for isothermal, we need constant temperature. That's why. 2 moles of an, see here you have initial volume is getting half. So what will happen to final temperature? If initial temperature is 300 Kelvin, so this is isothermal process. It's not mentioned over here. This has to be mentioned. It's a part of question, isothermal process. So in the first part, final temperature will be 300 Kelvin only, because in isothermal process, temperature do not change. Then you have P1 V1 is equal to P2 V2 for calculation of final pressure. So see here, initial pressure is given as 1 atm. Final pressure you have to find out. Initial volume is, let's say, V. So final volume will become V by 2 because it is becoming half. So put it in the formula. This is 1 into V is equal to P into V by 2. So pressure is equal to 2 atm. Lastly, you have to find out work done. So you will use the formula 2.303 nRT log V2 by V1. So this will be equal to 2.303. Number of moles are 2. Constant's value is 8.314. Temperature is 300 log V, and the V by 2 is final volume and initial is V. So this becomes log half. So log half means what? 1 by 2. So it's like log A by B. What did I tell you? This is log A minus log B. That is log 1 minus log 2. So this will be 2.303 into 2 into 3, 8.314 into 300 log 1 minus log. So work done is equal to 2.303 into 2 into 8.314 into 300. So log 1's value and log 2's value is given to you from the question. Look here, this is log 2 and log 1 is 0. So this becomes 0.3010. So this minus sign will also come now, because here it is 0 minus 0.3010. So minus sign will come. So your final answer on calculation will become minus 3457 joules. Note it down. One more question we'll see if time permits. Question, if you have not noted, let me know. I'll scroll it up. See, in this question, it is directly stated slowly. So it means definitely this is isothermal process. So whatever is the initial temperature, that is going to be the final temperature. So final temperature will also be 100 Kelvin. Now you have to find out again the final pressure. So P1 V1 is equal to P2 V2 you will apply. So P1 is 1, V1 is V. Final pressure we have to find out, and final volume is 1/3, that is V by 3. So V cancel, again pressure becomes 3 atmospheric pressure. Last is work done. So work done is equal to 2.303 nRT log V2 by V1. So this will be 2.303. N is 10. R is 8.314. Temperature is 100. This becomes log V by 3 into V. So here this time, that time it was 2. Now it is 3. So when you'll put in the values 2.303 into 10, I'll write down the value only itself. 19147.14. This becomes log 1 minus log 3. So your answer is minus 19147.14 multiplied by 0.477 with the minus sign. So that will be 9133.1 joules. That will be the work done with the negatives. Fine, note it down. Text me done once completed.